Hello. Today I'm going to talk to you about Beer-Lambert's law, also known as Beer's law, and just a little bit about spectrophotometers and the absorbance data that we can get from them to determine concentration. So first of all, in lab, we would make up a maybe 5 different solutions of a colored ion, like copper +2. That's what these are. So if I had about 5 different samples of these, then I will take the absorbance of them. I know the concentration, and then I can make a graph of absorbance versus concentration. So you might have done this in lab before. So that's what we're doing right here. So a graph of absorbance versus concentration will allow us to then get the slope of that line. And that E is the molar absorptivity constant that relates concentration to absorbance for that particular ion. So for the colored copper +2. And so just a little bit of background. I'm sure that you all know that, for instance, if you have a green sample, that it means it's reflecting green and that all the other colors are being absorbed. But sometimes our students aren't quite sure why we pick a particular wavelength of light to shine through. So I think that's important to make sure that they understand that. So the complementary color of green is red. So we would want to shine red light through here to get maximum absorption. And that's about 700 nanometers. And depending on what color your sample is, if it's cobalt, so cobalt samples are pink. Oh, there it is. And so for cobalt, the maximum absorbance is right around 500 nanometers, which is green. So, and green is the complementary color for pink. So sometimes there's even questions about that, like what would be the maximum absorptivity wavelength for different samples. And so we put our sample in a cuvette. A cuvette, if you haven't used a Spec 20 before or another type of spectrophotometer, it could be a little test tube, it could be a little square um, container, whatever, for that machine. So you put your sample in there, and then you choose your wavelength. And so inside the machine, there's a prism that will pick. You're able to pick a specific wavelength of light, the complementary color of whatever color sample you have. So this will not work for samples that are not colored. Okay, if it's a clear sample, it doesn't work. It has to be something like cobalt or copper or other transition metals that have color. And so we're putting our sample in there. If the sample is very concentrated, then a lot of light will be absorbed, less light will be transmitted. So if these were like all the little particles and we're shining light through there, well, less will come out the other side if a lot is being absorbed. So in a concentrated sample, less light transmitted, higher absorbance, versus in a dilute sample where there's less particles, then when you shine the light through, most of it will just go straight through. So it would have a lot lower absorbance value. And I'm sure you know that. It's just that just a good reminder. Make sure that your students are understanding that because you may or may not actually do a lab like this. And so the amount of light absorbed, again, is directly proportional to the concentration of the sample. So then we have Beer's law, which is absorbance equals E times B times C. And absorbance doesn't have units, capital A. E is the molar, I can't say this word very well, absorptivity. It was previously called the extinction coefficient or the molar extinction coefficient. The units for that are liters per mole per centimeter. And so then B is path length, and then that needs to be in centimeters if to match the E that is per centimeter. And that's the width of the cuvette that the light's traveling through. And then C is concentration, molarity. So again, when we graph A versus C, we have this slope of the line is equal to the E times B. A lot of times if path length is constant because you're measuring all of your samples with the same spectrophotometer, then you can ignore B and you will just have that E is the slope of the line. And then that's your relationship. And you can take any other sample, measure its absorbance, and calculate its concentration. So on the Olympiad test, there are various questions. This first question that I found was from the 2012 National Part 1 exam. And I'll just read it. An acidic solution of methyl red has an absorbance of 0.451 at 530 nanometers in a 5 millimeter cell. Calculate the molarity of methyl red in this solution. And then the molar absorbativity is 1.06 times 10 to the fifth liters per mole per centimeter at 530 nanometers. So first of all, the kids need to understand that they don't need to do anything with the 530 nanometers. That's not in the equation. It's just telling you at what the wavelength of light was that was sent through. And then as we look at what is given, again, since E is per centimeter, and they gave you the cuvette cell as 5 millimeters, you have to convert the 5 millimeters to centimeters. And then you're just plugging in A divided by E times B, and you come up with an answer of 8.509 times 10 to the negative 6 molarity. So then looking at the choices, C is correct, 2, 3 sig figs. Okay, so that was one question. Another one from the 2000 Olympiad test, this was the local exam question 15. A 20 mil sample of copper plus 2 was diluted to 250 mils. A portion of this solution was found to have an absorbance of 0.15 under the same conditions that were used to generate the given absorbance versus copper plus 2 graph. What was the concentration of copper plus 2 ions in the original sample? All right, so looking at the graph, we would say, okay, so 0.15 was the absorbance, so 0.15 going over to the line, coming down. Oh, so that concentration is 0.075 molar. And you look at your answer choices, well, guess what? That is an answer choice, but that's not the correct answer because that was the concentration of the dilute sample. So they were a little tricky here. It does say what's the concentration in the original sample, but you know how it is. A lot of kids will see that 0.075 and they'll think they're done because that's one of the answer choices. So again, really stressing, well, you're not done. So I have it worked out on my next page. Let's get rid of this. So on the next page, I show that I would just use then the dilution equation. So we just found out that it is 0.075 molar for the 250 mils, the diluted, but then we can plug that in on the diluted side, molarity of dilute times volume of dilute. But then on the concentrated side, we just have the volume. It was 20 mils used. And then we're solving for the molarity of the concentrated because that is what the question's asking. So when we multiply and divide, we get 0.94. So answer choice D was the correct answer of 0.94, not the 0.075. Okay, so that one, it was not just understanding what they were doing with the graph and reading the graph. You then had a little bit extra in there. They put molarity in there too, or dilution in there too. So then the third example I have was from the 2021 Chemistry Olympiad National Exam Part 1, question 12. A student performs an experiment to determine the concentration of a colored salt solution by measuring the absorbance of the solution at the wavelength of maximum absorbance of the salt and using Beer's law to calculate the concentration. Which of the following could cause the measured concentration to be higher than the actual concentration? A, the cuvette is not rinsed with the salt solution after being washed. Okay, well that one, if you've actually done this experiment, you know that you put your sample in, you are usually only have one cuvette. So you put your sample in, you measure it, you dump that out, and then you're always supposed to rinse with the next solution that you're measuring, because if you had just washed it with water and there's still water in there and then you put that in, it's going to dilute it. Or if there was a previous sample in there or whatever. So you always pour a little in, rinse it out, dump it, then fill it. So in this case, if it was washed with water and then they just dumped theirs in, they would have diluted it. So it would be lower than the actual concentration. B, the cuvette is not wiped off before it's inserted into the spectrophotometer. So now again, we're thinking of this cuvette, and if we're holding it and we fill it and then we get our fingerprints on it, then we stick it in, as the light's going through, it's going to be partially blocked by the fingerprints. Well, the machine is going to register lower transmittance of light, so it's going to seem like more light got absorbed. So that also would make it seem like the concentration is higher because less light will be transmitted. So the absorbance would be higher. So then they would get too high. So that is the correct answer. C, less than the recommended volume of salt is added to the cuvette. Okay, that would also be lower. They wouldn't have as much in there. And D, the wavelength is set to a different than the maximum wavelength. So it would be at a wavelength where it wasn't absorbing as much light as the maximum wavelength. So again, that would be too low. So B is the only possible answer that would give a higher concentration. All right, so I hope that would help. If you had any questions on how Beer's law is used and a little bit of spectrophotometer stuff used in the Chemistry Olympiad.